Okay, good evening. It's March 2nd. The time is 11:52 p.m. It's almost 12 o'clock. Okay, my discussion for tonight will be an interesting one. It's the worst case scenario problem under electrical transients. That is a combination of a resistance, inductance, and a capacitance. They are in series and energized by an alternating current source. Okay, I will check my camera. Oh, it's fine. Okay, let's proceed. My lesson for tonight is advanced mathematics, and we are now on lesson number 15. We are on the application of the so-called non-homogeneous differential equation. So our topic for tonight is advanced math, lesson number 15. We are on the application. The application circuit is a resistance, inductance, and capacitance. They are connected in series, energized by an alternating current source, that is the voltage is E sub m sine of the quantity omega t plus angle p. So meaning our circuit for tonight is series, resistance, inductance, and capacitance, alternating current circuit. And the requirement of the problem is find current as a function of time. For current as a function of time for this circuit, there will be three cases. So actually the solution is a little bit long. So later on, I will try to flip over my magnetic board to show you the other computations as we continue the solution. Okay, let's proceed. To find for current as a function of time, as always, we will take the summation of voltages around the closed loop as we close the switch, and this should be equal to 0. That is plus E minus B sub R minus B sub L minus B sub C, and this should be equal to 0. Okay, all the negative terms on the left, I will put it on the right, then I will try to rearrange. So what will come out will be B sub R plus B sub L plus B sub C, and this should be equal to E. The voltage across the resistance will be the current passing times R, so this is IR. The voltage across the inductance, it's from physics actually, it is actually the inductance times the rate of change of current with respect to time. And the voltage across the capacitance, it's more a complicated thing. It is actually 1 over C, the integral of I dt, and this should be equal to, the power source is alternating and the voltage is actually E sub m sine of the quantity omega t plus angle p. Okay? So to bring out the so-called differential equation that will give us the solution of the problem, we must have to eliminate this integral signs here. And to eliminate the integral sign, we will take the differential. The enemy of the integral sign is the differential. So if we take the differential of all the terms, okay, it will be RDI plus L, okay. We will take the derivative of I again, so that will be d square I over dt. Dt is not yet square. We are only taking the derivative of I. So this will be L d square I over dt plus 1 over C. The integral of the differential of I dt will just be simply I dt. If we take the differential of the integral of I dt, this should be equal to I dt. Because as I have said before, and also for tonight, the integral and differential sign are actually anti-derivative, or this derivative is anti-integral, so they will try to cancel out. So after taking the differential, we eliminated already the integral sign. So what comes out for the third part on the left will be 1 over C. The integral of I dt equal to, for the right hand side, we will take the differential. E sub m is constant, this is a sine function, so it will be e sub m. The derivative of sine is cosine. Oh, what? Sorry for this one. This should be cosine. This should be cosine. Okay? Because we took the derivative already. So it will be e sub m, the derivative of sine will be cosine of omega t plus angle p, times the derivative of the total angle. The total angle is actually omega times dt. The derivative of angle p is actually constant. So if we take the derivative, it will be 0. So the multiplier on the right will just be simply omega e sub m cosine of the quantity omega t plus angle p times differential time. Okay? We are taking the differential. Okay? Time is variable, so this should not be times 1. It should be differential time. And to simplify calculations, we will multiply all the terms by the ratio 1 over dt times L. Okay? And if we try to distribute, okay, r times 1 over L dt will be r over L di dt. There is a dt now on the first part, okay, because there is a dt here. Second part, okay, this L here will vanish because there is an L over there. This is d square I, but this is dt times a dt, so this will now be dt square. So this is now actually the second derivative of current with respect to time, that is d square I over dt square. This is actually I double prime. Okay? The third part on the left will be 1 over c. There's a dt here, right? So this dt here will disappear. And 1 over c times 1 over L, it will be, this should be, sorry for this one. There should be an L over here. That's my second error, okay? So this should be 1 over LC times I. I will shut off my alarm. It's 12 o'clock, okay? The third part on the left should be 1 over LC times I. I put only C a while ago. That's the syntax error. 1 over LC times I equal to, for the right hand side, this dt will vanish, right? So it will be omega e sub m over L times the cosine of omega t plus angle p. Okay? And if we try to rearrange, we'll take the second derivative first. D square I over dt square plus the ratio r over L times di dt plus 1 over LC times I equal to omega e sub m over L cosine of the quantity omega t plus angle p. This is now actually a second order differential equation. The right hand side is not equal to 0. So supposed to be the resulting second order differential equation is non-homogeneous. So we are expecting a worst case, total solution. It comprises of the so-called complementary plus the so-called particular solution. And also, there are three possible cases. Okay, I will check my camera again. Okay. Okay, let's try to bring out the complementary solution. As always, the complementary solution for a non-homogeneous will be ke to the mt. First derivative will be km e to the mt. Second derivative will be km square e to the mt. Take the second derivative, first derivative, and the value of IC, we place it back here. Then we equate the right hand side to 0. So what will come out will be km square e to the mt. I'm following this. Plus r over L km to the mt plus 1 over LC ke to the mt equal to 0. There are some common terms. So we will multiply this by 1 over k e raised to mt. Okay? If we try to expand this one by multiplying all the terms by this, what comes out on the first one, this k here will disappear, a to the mt will disappear. First part will just be simply m squared. Second part, k will disappear, e to the mt will disappear. Second part will be just simply the ratio r over l times l. Third part, this will totally disappear. What remains will be a pure constant, 1 over LC. Pure constant because the inductance and the capacitance, if we try to multiply two constant, it will be constant, and 1 over a constant will still be constant. So this is actually a pure constant, equal to 0 times 1 over k e raised to mt will still be 0. So we are now given the characteristic equation, and unluckily, it's a quadratic equation. Okay? For the solution of the quadratic equation, we will just discuss the possible three cases. Okay? If m1 is equal to m2, by using the quadratic equation, m1 will be alpha plus beta, m2 will be alpha minus beta. They are both real, and they are not equal. So I place it here, m1 is equal to m2. So the solution, if it falls under case number 1, using the quadratic equation, this will be the solution of the complementary. That is e raised to alpha t times the quantity k1 e raised to beta t plus k2 e raised to minus beta t amperes. That is for case number 1. For the meantime, I have not computed for the value of m1 and m2 because we are not given a specific problem. This is just what I call this, a general solution. For case number 2, if m1 is equal to m2 and they are real, okay, m1 should be equal to m2 and they should be equal to alpha. For them to be equal, the second part should be equal to 0. This one, this one. Because if the second part will be 0, this will vanish, and this will vanish, right? So m1 is equal to m2, and it is equal to alpha. So for case number 2, m1 and m2 is alpha, beta is 0. And the general solution of the complementary solution will be e raised to alpha t times the quantity k1 plus k2 t amperes. That is for case number 2. They are both equal and they are real. For case number 1, they are real but unequal. And for case number 3, this is the worst case scenario also for the complementary solution. Because for case number 3, if the resulting value of b squared minus 4ac on the quadratic equation come out to be so-called a complex conjugates, m1 and m2 under case number 3 are actually complex conjugates, meaning there is an imaginary part. That is, m1 is actually alpha plus j beta, and m2 will be alpha minus j beta. There is a g over here because the sign of the term inside the square root for the quadratic equation is negative. So whether we like it or not, the resulting m1 and m2 will be complex conjugates. That is, m1 is alpha plus j beta, m2 will be alpha minus j beta. So the total complementary solution will be this one. E raised to alpha t times the quantity k1 cosine of beta t plus k2 sine of beta t close quantity amperes. So for the complementary solution, there are 3 possible cases: case 1, case 2, and case 3. Later on the total general solution, we will try to consolidate case 1, case 2, and case 3, including the required particular solution. Okay, let's proceed with the particular solution. For the particular solution, it's the same from the last discussion. I particularly will be a cosine of omega t plus angle p plus unknown constant b sine of omega t plus angle p. First derivative, it will be negative a omega sine of omega t plus angle p. If we take the derivative of cosine, it will become negative sine, so this is now negative. And the derivative of the angle is omega, so the total first derivative is negative a omega sine of omega t plus angle p. Second part, the derivative of sine will be cosine plus, so this is still a plus. Okay, so this should be b omega cosine of omega t plus angle p. Taking again the derivative of the first derivative, okay, the derivative of sine will still be cosine, okay, so this is still negative. And again, we will take the derivative of the angle, so this will now be negative a omega square as a coefficient of cosine of omega t plus angle p. The derivative of cosine is negative side, so this is now negative. So we repeat the omega, so this should be negative b omega square sine of the quantity omega t plus angle p. Substituting values. The first part is actually this one, the value of the second derivative. The second part will be the value of the first derivative. The first derivative is actually with the coefficient r over L, right? Times the first derivative. This is the first derivative. This. And the third part on the left, it will be 1 over LC. So this is 1 over LC. Times I, the particular, which is actually A cosine of omega t plus B sine of omega t plus angle p, closed quantity. And this should be equal to, for the particular, we will take the right hand side. It will be omega e sub m over L cosine of omega t plus angle p. And equating coefficient of like pairs, I will try to expedite a little bit so we could flip the word. Okay. For all the terms with that contain sine of omega t plus angle p, the coefficients are this one. Negative b omega square a omega r over L plus b over LC. You could check it. For the sine of omega, the first coefficient is b omega square, right? So that's one. The next sine of omega t is this one. So the coefficient will be negative omega r over L. So this is negative a omega r over L. This is the product of this. And the last sign will be this one. 1 over LC times B. So this is actually B over LC. Right hand side, there is no sign. So this should be equal to 0. And if we try to compute for the value of B, we simplify this one. I didn't show you the complete simplification. But if we try to compute for B, this will be V. As a function of the unknown constant A, plus the circuit parameters, that is B is actually AR, excuse me, times the difference of XC minus XL, where X of C is actually 1 over omega C, the inductive reactance, and X of L is actually omega L. So for the cosine of omega T plus angle P, we equate all the terms. The coefficients will be negative A omega square plus BW R over L plus A over LC, and this should be equal to the right hand side, omega E sub m over L. Actually, we check the first one. The first cosine is actually this one, and the coefficient is negative omega square. This is. And so on. Okay, the right hand side is actually omega E sub m over L. This is cosine. Okay. This is A. If we try to simplify this one, okay, what comes out for A will be this. Okay. I will continue on the flip of the word. Sorry for this one. I will flip the word. I will check the alignment of our camera if it's still okay. Oh, it's still okay. It's still okay. Oh yeah, it's still okay. Okay, we continue. If we try to simplify B from the previous word, this is B. And from the cosine function, this is the equation, right? If we substitute B to be this back here, what will come out for A will be E sub m over C square times the difference X sub C minus A sub L. And again, since this is A, we try to modify the equivalent of B in terms of all the terms. So B now will be, I will follow this, ER times the difference XC minus XL. Okay, but B is A is actually this one. So if we put A to be this one here, B now will be the simplified form of B. The unknown constant B will be E sub m times R over the impedance square. We needed these values, okay? So the particular solution now will be, what do you call this? E sub m over c square, okay, times the difference x sub c minus e sub x sub l cosine of omega t plus angle p, okay, plus e sub m r over c square sine of omega t plus angle p. This is actually A, and this is actually B. See, right? And if we try to manipulate this one, we could place this one as E sub m over z times the difference of x sub c minus x sub l over z cosine of omega t plus angle p plus the ratio r over z sine of omega t plus angle p, close bracket. That is just a simplification, okay? Algebraic manipulation. I will check my camera. Okay? Okay, let's try to bring out the two cases for the possible solutions of the particular solution. For case number one, if the circuit is capacitive, meaning capacitive is the capacitive reactance is greater than the inductive reactance. X of C is capacitive reactance, X of L is inductive reactance. So X of C is X of L, that falls under case number one. Okay? So under case number one, the net reactance of the circuit, it's easy circuit, it will be the difference of the capacitive minus the inductive. The capacitive reactance is greater than the inductive reactance, so the net reactance will be X of C minus X of L. And if we try to bring out the vector diagram of the impedance, this is the resistance, this is the net reactance, this is the impedance. And then here, the sine of angle theta will be this side here over Z. It is this. Okay? And the ratio R over Z is actually cosine of this angle, R over Z. Oh, that's what you call this trigonometry. So if we try to go back here, it will become E sub m over Z times the quantity X of L minus X of C cosine of omega t plus R over C sine of omega t plus angle p. But this ratio here is actually sine of theta. That's sine of theta. And the ratio R over Z is cosine. It comes from this. So we replace X of L minus X of C minus X of L over Z by sine of theta. Cosine. R over C will be cosine of theta, sine of omega t plus angle p. And if we try to compress this one, this emanates from the expansion of the quantity sine of the quantity angle A plus angle B, where angle A is equal to omega t plus angle P, and angle B is actually angle theta, the angle of the impedance. Okay? So the compressed equivalent of this will now be sine of the quantity omega t plus angle P plus angle theta. That is, I particular for case number one will be E sub m over Z sine of the quantity omega t plus angle P plus angle theta. Oh, this is a plus over here. And the significance of the plus, it is leading. Leading meaning the circuit is capacitive. Okay? If we try to draw the graph of the current with respect to the voltage, the current will be leading. So that's plus. That's the significance of the plus. So the particular solution for case number one will be E sub m over Z sine of the quantity omega t plus angle P plus angle theta. Okay? Okay, let's try to bring out case number two. For case number two, if X of L is greater than X of C, we could say that the circuit is inductive. Meaning the motor loads are greater than the capacitive loads, or maybe the synchronous motors. So if we try to bring out the vector diagram of the impedance, this is A, this is R. So for case number two, if X of L is greater than X of C, we could rewrite this X of L minus X of C as a negative open quantity X of C minus X of L. Okay? And if we try to compute for the value of sine of theta will be this side here. This will be negative. Right? No negative yet. It should be negative open quantity X of C minus X of L over Z. And if we try to eliminate this one, we put the negative on here. Meaning negative sine of theta will be the ratio of x of c minus x of L over c for case number 2. And cosine of theta, it doesn't change. If theta change, it will just be simply the ratio r over c. So cosine of theta for case number 2 is still r over c. So if we try to go back here, it will now be e sub m over c. But the ratio x of c or x of L, x of c minus x of L over c will be negative sine of theta. Okay? There's a negative. So negative sine of theta, cosine of omega t plus angle phi. The cosine is still a plus. A cosine of theta, sine of omega t plus angle phi. And actually, if we try to compress this one, the second part is actually negative. And this is actually the expansion of the quantity sine of A minus B, where A will be omega t plus angle P and B will be equal to angle theta. So if we try to expand this one, this is the expansion. And if we try to compress this one, IP now will be A sub m over c. The compressed equivalent of this will be sine of the quantity omega t plus angle P minus theta. For case number 2, this should be minus. Okay? For inductive, minus. So the significance of this negative here will be lagging. Meaning the total particular solution lags the applied voltage by this certain angle theta over here. So the significance of this negative here, it means lagging. So the total equation for the particular solution for case number 2 will be E sub m over c, sine of the quantity omega t plus angle p minus theta amperes. I will check my camera again. Okay, let's try to bring out the total general solution for an RLC energized by an alternating current source. In general now, the total current for the complementary solution, the first part is case number 1, the second part is case number 2, the third part is case number 3, plus the particular solution. In our particular solution, there are two cases. It will be this one here, or this, right? So I place it here already. It should be E sub m over c, sine of omega t plus angle p. If we try to use the plus sign, that falls under case number 1. If we try to use the negative sign, it falls under case number 2. So I place it here for simplicity. The total particular solution for both case number 1 and number 2 will be E sub m over c, sine of the quantity omega t plus angle p plus or minus theta amperes. So this is the total solution of an RLC circuit, okay, alternating current. Okay, that's it, guys. So for those who are taking advanced mathematics, this is for you guys, okay? If you want to subscribe to my channel, okay, I got long-form videos on differential calculus, integral calculus, differential equation, and this is now the fourth long-form video, advanced mathematics. This is for you guys. If you want to subscribe, my channel is at youtube.com/@ProfDavidJDeLosReyes. And if you want to share it, please click share. Good evening from Los Angeles.